Hey guys, today we're going to learn about rotational inertia. Rotational inertia is the resistance of an object to changes in its rotational motion. And it turns out different objects have different amounts of rotational inertia. So I want to start off with a demonstration here. I have two pipes and they are different weights because this one is made of solid steel and this one is just made of PVC plastic, but they're both hollow and they're both about the same size. And my question to you is, which one will roll down the hill faster? The heavy one or the light one? The way we're going to do this is we're going to stack these here and we're going to release them and see which one goes faster. All right, so have a guess in your mind, heavy one or light one. And as we can see, they go pretty much the same speed. I am unable to release them at exactly the same point, but you can tell they stay together pretty well. So they're rolling down the hill pretty much the same rate. Now let's try two that are the same weight. So this is solid steel, like I said, hollow pipe. This one is PVC, but it has a steel core inside it. So the weight of this one, or the mass of this one with the stuff inside, is the same as the mass as the solid steel one. So again, make a prediction. Which one do you think is going to go down fastest? Or again, will it be the same? They are the same weight this time. Okay, here we go. If you have your prediction. That's interesting. All right, so what we see is the object with its mass concentrated in the center is easier to spin than the one that has the mass all just distributed around the outside. So even though they have the same mass, they have different resistances to changes in their rotation. It's easier to turn this one because it has its mass at the center, and it's harder to turn this one because its mass is all around the outside. One last demo here. Let's see if you can make a prediction. I have a hoop and I have a solid disc. They're the same mass. And when I put them on the table here, which one is going to roll down fastest? The hollow one or the solid one? Here we go. And the solid one goes faster. Hey guys, today we're going to learn about rotational inertia, or what is also sometimes called moment of inertia. So those two terms are interchangeable. They mean the same thing, and I'll be going back and forth between them, so don't be confused when I use one or the other. In your book, they talk about moment of inertia, but I find that kind of unintuitive, non-intuitive. Rotational inertia really does a better job of describing the concept. So you do see them both used in different sources, but our book mostly uses moment of inertia. So we're going to see what it is, and we're going to see how we use it in a couple problems here. All right, last time we talked about torque, and I said that torque was the rotational equivalent of force, where force is something that makes something, changes the motion of something in a straight line, while torque is the rotational force that changes the rotation of something. And I said when I showed you this one, hey, there's also this one down here, and I'll get to it another day, and today's the other day. So mass is the characteristic of something that resists changes in its motion. So if something has a lot of inertia, you have to push on it real hard to change its motion in a straight line. Well, rotational inertia is the same idea, but for rotating objects. So if you have a bicycle wheel, it's not turning. Yeah, if you have a bicycle wheel, it's not turning. And if you put a torque on it, it will begin to turn. But different wheels, different objects have different resistances to changes in their rotational motion, just as different objects have different resistances to changes in their linear motion. Okay, so again, torque is analogous to force. Rotational inertia is analogous to mass or inertia. The basic equation for rotational inertia is this one right here. I is equal to mr squared. All right, and I is the rotational inertia. M is the mass of the object, and that has to be in kilograms. And r is the distance or the radius of the object, the center of mass of the object, center of mass of object, to the center of rotation. I'll show you what that means in just a second. But the units of this are going to be meters, and since it's squared, we're going to wind up with meters squared. And that means that the units of rotational inertia, or the units of moment of inertia, are kilogram meters squared, which is kind of a weird unit, but that's the way it works out. Okay, now what do we mean about this center of mass? Suppose that we have a ball on a string, okay? And we are going to spin this ball around in a circle. Okay, so we're going to assume, just to simplify it, that the string has no mass, and all of the mass is in the ball itself. Let's call this 1 kilogram. That's called to be a 1 kilogram mass. All right, and if this is, let's say, 0.7 meters, then r is 0.7 meters. And it's the distance from the center of mass of the thing which is spinning around and around to the point that it's spinning around. Okay, so we can plug some numbers into this as we already have. We can work this out. So the rotational inertia of this object in this situation is going to be equal to the mass, so it's 1 kilogram times 0.7 meters quantity squared, which comes out to be 0.49 kilogram meters squared. Not very complicated, it's just a straight plug-in. All right, now what complicates things here is that different objects have different rotational inertias because of the way their mass is distributed. Okay, and I'll show you what I mean here in a second. Which means that this equation that I've just showed you, this is just the most basic equation. There's actually dozens of these or hundreds of them, depending on the object that you're trying to spin and the way you're trying to spin it. And again, this will be clear as I move on here a little bit, but this is just the most basic one, where all of the mass is concentrated at one distance away from the center of rotation. This equation also applies to another specific shape, and that is if you have a hoop, okay, that is rotating around its center. So something like this. This is a pipe, and all of the mass is concentrated around the edge of this thing. And if I try to rotate it like this, the equation for this rolling or rotating in this manner is the same, because all of the mass is concentrated the same distance from the center of the pipe. So it's as if it's an accumulation of a whole bunch of these balls on strings, all strung together around a giant hoop. So this number, by the way, is a measure of how difficult the object is to get rotating. So if this number is big, it's hard to get it rotating. If this number is small, it's relatively easy to get it rotating. So just by looking at the number, you can compare different objects. All right, now on page 210, there is a table of different shapes and the equations that go with those shapes. I'm going to use this one here because it's a little larger and I think it'll be easier to see on the camera, but page 210, you have access to this thing. All right, so for example, this is the cylindrical hoop that I was just showing you. This thing has a the formula for it is mr squared. Now, we don't have the formula on this page, but if we were to take this same hoop and instead of rotating it like this, if we were to rotate it like this, it's going to be a different number. It's going to be a different equation because now some of the mass is at the center of rotation and some of it is part way out and some of it is all the way out. So we have to find some kind of an average distribution of where the mass is and make a formula based on that. So Another one here is a solid sphere. So like a golf ball that has mass all the way to the center, the equation is 2/5 mr squared. For a hollow sphere, you can't quite see, but they have a dotted line around here. So this would be like a ping pong ball or a tennis ball. In that case, all the mass is concentrated around the outside. There's none in the middle. So that turns out to be 2/3 mr squared. So you would take the mass of the whole thing, you'd take the radius of the sphere itself, and then you'd square it and multiply it by 2/3, and that would give you the number that you'd hang on. Okay, a solid cylinder, so something more like this, where you have mass all the way through the thing. If we rotate it like this, we would use 1/2 mr squared. So depending on the shape of the object and the way we are trying to rotate it, we have different equations. So when we look at an object, we have to kind of approximate which formula we can use. And we can use these in combination, which I'll use in a moment. But yeah, so if I'm swinging it like this, that's this formula. If you swing it like this, it's this formula. So 1/12 versus 1/3 ml cubed. Same thing with flat plates. Let's imagine a hammer. Okay, so we have a hammer that has a wooden handle and it has a metal head at the top. And let's say that this metal head is 0.75 kilograms. And we're going to say that the handle is 0.25 kilograms. And we're going to say that the length of this thing, we're going to put the handle embedded into the head a little bit. We're going to call that 0.3 meters. That seems like a good number. Okay, so we don't have a formula for a hammer, but we do have a formula for a stick which we swing from the end. And when we swing a hammer, we can approximate that as saying that we are pivoting it from this point and making it swing like this. So we can do one calculation to find the rotational inertia of the handle, and then the head of the hammer is 0.3 meters from the center of rotation, and it is more like the original thing we looked at. So it's all of the mass is concentrated out here, the same distance from the handle. And since the units of these are the same, the units of moment of inertia are the same, we can just add them together and get the total moment of inertia of the object. So let's do the handle. The formula for that is 1/3 ml squared. That's this formula right here, and it's in your book as well. And then the head is just mr squared. It's the simplest one of all. So we get 1/3 times 0.25, that's the mass of the handle, times the length of the handle, 0.3 meters, quantity squared. And the head is the mass, which is 0.75 kilograms, times 0.3 meters squared. I'm running myself out of room here, so that's all right. Let's take this down here. This comes out to be, so we're going to do the math on this, and we get 0.25 times 0.3 quantity squared, and we're going to divide that by 2. So for the handle, we get 0.01125 kilogram meters squared. And for the head of the hammer, we get 0.75 times 0.3 quantity squared equals 0.0675. And we just add them together, plus 0.01125, and we wind up with 0.07875, which we can probably round off to 0.079, is equal to the moment of inertia for the hammer. Okay, I think that will be enough to get you unstuck, that with the examples that they have in the book for the homework, and we'll see you next time.